All right, come on. This is the worst start so far. Can you listen to what I'm saying, please? Anybody have any other homework questions? Okay. So last time we started talking about kinetics. And particle kinetics combines everything we know about kinematics with causes of the motion. And the most important equation for kinetics, the most important equation in this whole class is Newton's second law. That says that if you add up all the forces acting on a chosen body, that's equal to the mass of the chosen body times the acceleration of the chosen body's center of mass. This has to be true for any inertial coordinate system. And the thing with the inertial coordinate system, we saw that video where the video was taken from a non-inertial coordinate system, an accelerating bus, and you got that behavior that if you were doing calculations based on measurements, Newton's second law wouldn't apply. So what's required for a coordinate system to be inertial? Yes? It can be moving. It's a specific kind of moving. Yeah, okay. So an inertial coordinate system is not accelerating and not rotating. And so what that means is, well, what's the acceleration if the velocity is constant? Zero. Constant velocity means zero acceleration. So a coordinate system can be moving with a constant velocity, and measurements taken in that coordinate system will still satisfy Newton's second law. Okay, that's sort of so in that video we watched last time, so we saw a video taken from a camera that's mounted to the bus. Okay, that's an accelerating coordinate system. Newton's second law doesn't work. But if you watched what happened from a camera, say the bus had enough windows that you could see what was going on through the windows, and you had a camera just sitting on the street watching what happened and took measurements based on that, it would look like Newton's second law was satisfied, okay, because something sitting on the street, it's not accelerating, not rotating. What if you had a camera that was in another car going by at 50 miles an hour? As long as it's staying in a straight line and the velocity is constant. Well, what you would see is the person, it would look like the person was moving that way at 50 miles an hour or whatever. But the accelerations and the forces would match. It would just look like the person was moving backwards fast to a camera that was mounted on another car moving. So a coordinate system that's moving with a constant velocity will take perfectly fine measurements, which is good because we don't have any way of knowing like what the velocity of the Earth is. You know, it could be moving, 1,000,000 miles per hour compared to some faraway galaxy or whatever. We have no idea. One other thing. So inertial coordinate systems are not accelerating and not rotating. Wait, isn't the Earth rotating? Yeah, what if this was the end of physics right here? Well, it is, but not very much, not very fast. So the surface of the Earth is moving fast, but if you think of the speed of rotation in terms of an angular velocity, the Earth is rotating really slowly. We go 2 pi radians every 24 hours. So right, right. So 2 pi radians for every 24 hours, where 1 hour is equal to 3,600 seconds. So you end up with like something like 0.00, no, just 0.01 thousands. Yeah, can someone just calculate that? Yes. If what? Okay, yeah. So what is it? 0.0016 repeating or something, right? Forgot about the 24. 0.0007 something. Okay, radians per second. So, anyways, even though the speed of the surface of the Earth is high, because the radius of the Earth is so big. But what really matters, and we haven't talked about this, how this comes up, but what really matters for making it non-inertial is this angular velocity, and that's a really, really small number. And so the Earth is not an inertial coordinate system. If you put a camera on the Earth, you're not getting measurements from an inertial coordinate system, but it's really close because that's so small. So yeah, if we take our measurements based on a camera fixed to the Earth, we get pretty good results. Good enough for most experiments. You can do experiments that detect that motion of the Earth. Yeah, and there's a way to cancel it out, exactly. But for anything we do, we're going to assume that the Earth is an inertial coordinate system. So that's tiny. So for our purposes, coordinate systems fixed to the Earth are inertial. Okay. Let me do one example. So let's say that we have a particle that's moving according to the position function 2t squared t cubed plus 6. And this is in meters and seconds. And we want to calculate the net force as a function of time. Well, since Newton's second law, the thing that connects force and mass to our kinematic results deals with the acceleration, we need to use this equation to come up with an acceleration function, and then we can just use Newton's second law. Okay? So velocity vector is a function of time. Velocity is the time derivative of position. So 4t, 3t squared. The acceleration as a function of time is equal to 4, 6t. And so Newton's second law says F net at any instant is equal to the mass times the acceleration of the particle, which is 4m 6t, or write it as 6mt. Okay, so if the particle has a very small mass, it doesn't take that much force to keep it moving according to that position function. Mass. That's the mass of the particle.
So basically, mass is mass times the acceleration.
The mass times the acceleration of the particle's center of mass. Yep. So we use the position function to figure out the acceleration function, and then we multiplied it by the mass, and that gave us a function for the net force. And you can see if the mass is big, you need a big magnitude net force. If the mass is small, you need a small magnitude net force. So if all you want is the net force, then all you have to do is multiply the acceleration vector times the mass. Usually that's not what we want, though. Usually we want to separate the net force up into the individual forces that make it up. Usually, though, we want to separate F net into individual forces. And so to do that, the first step is to draw a free body diagram of the chosen object. Okay, so free body diagram of the chosen object. And so I want to talk first about free body diagrams. I'll abbreviate that FBD. The free in free body diagram means that we don't show any objects except the chosen object. You know, the only object we show is the chosen object. And other objects only show up as the force they apply to the chosen object. Okay, so the first thing we want to do is draw a closed outline of the chosen object. So here's an example. Let's say there is a car and on the roof there's a pig. Sort of looks like a fat cat, but the curly tail makes it clear it's a pig. Why does that look so little like a pig? No. What do a pig's ears look like? Do they point up? Do they point up or to the side? That's better, right? That's better than the first one. I'll leave it there. And there's a guy pushing on the front, trying to push it. Oh, and let's say it's trapped in the mud, because that's why he's pushing it. Yeah, pigs hate mud. If there's one thing I know about pigs, they are afraid of mud.
So is the chosen object the car? Is the pig in the...
We haven't said yet.
Oh.
And then, okay, this guy is trying to push this car out of the mud, and he has a harness around him, and there's a rope connected to the harness that's connected to a helicopter. Yeah, exactly. Okay. No, the helicopter, that helicopter is pulling the guy away from the car. The helicopter wants that car to stay in the mud.
What do we care about?
What? Yeah, so the first thing we have to do, so now this is the whole setup. Now we have to choose what our chosen object is. What are we going to isolate? Okay? We could, if we wanted, we could choose this whole system. We could choose the car plus the pig plus the person plus the helicopter plus the rope. Or we could choose any one of those, or we could choose a part of those. But let's say we want to isolate the car. Let's say the chosen body is the car. Then for the free body diagram, we just want to draw this. Closed outline. There are no internal details drawn. And no external objects. And the reason that we want to draw a closed outline is we want to be very clear about what's inside our collection of chosen things and what's outside. Okay, so we want to be very clear that we're isolating, when we isolate the car, we're including the windows and the wheels and the bag of apples in the trunk and whatever, but we're not including the pig or the person or the rope or the helicopter. Okay, so the idea here is that outline just very clearly breaks up the universe into what's in and what's out. Okay. Free body diagrams are super clicky. And then second, represent all forces applied to the chosen object as forces. And we'll show these forces represent all, yeah, that doesn't, represent all, let's just represent all forces applied to the chosen object. And we're going to show them as an arrow in the chosen direct, or in the direction of the force. With a scalar label, that can be a variable or a number, representing the magnitude of the force. Okay, so how do we know when we have all the forces represented? These forces are only made up of two types. The first is the weight force. You could also, you know, this isn't going to come up in problems in this class, but the other field forces, you know, force fields and super trends. Field forces like magnetic fields, electric fields. Yes.
like the answer.
Yeah, like it never occurred to them that maybe having a monkey in the most important command center in the planet might be a bad idea. Weak, right? Yeah, you have a good grasp of the Super Friends. Okay, so there's only two types of forces. The first is field forces. The one that's going to matter to us is gravity. There's gravitational field. So we'll represent the weight. And then the only other way that forces can be introduced is contact forces between the surroundings and the boundary that we drew. So, in other words, you'll show the force applied by gravity, and then you'll just go mentally around the boundary that you drew, looking for places where the surroundings make contact with the boundary. Okay, so if I go back to this car example, there's the boundary. There's a weight force. I'll call that the force of gravity. And then there's a force from the rear wheel. Yes? Yeah, that's the air making contact with it, yep. In this class, I don't think there are any examples in problems that we're doing, but yes. So there's the force on the rear wheel, and all I'm doing is going around, go around clockwise or counterclockwise and think of all the places that this boundary makes contact with the outside world. So if I'm going around counterclockwise, the next place that there's contact with the surroundings is the front wheel. The mud, I guess, would apply we'll talk about directions next, okay? It depends on, I guess it depends on a few things. But this is the force on the front wheel. If I keep going around counterclockwise, where's the next place where the surroundings make contact? Yeah, the man. So here's the force from the man. What about the rope or the helicopter? They're pulling on the man, so they don't occur in this. So it affects it indirectly, but that does not concern us. Yes? We're only dealing with the forces on our chosen object. And so the car is applying a force to the man, the car is applying a force to the mud, but we don't care about those. We only care about what the surroundings are doing. Yes? We'll talk about that next. So, really that wheel force, I suppose, would also be pushing, or there would be a force pushing back towards the man. I'm not going to worry about that yet. We'll do that later today. Yes? Yep, we just haven't gotten there in going around the boundary. That's pig. That's just... yeah, exactly. What did you say, chicken? My youngest son is just turned 7, and he in the last year was like, Dad, what? He was like, is chicken made out of pork? I was like, No, chicken is made out of a chicken. And he's like, no, 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 I'm talking about the food chicken. It's like, it's weird to like, you talk to people assuming like they see the world like you do, and then there's such huge differences in the way. And then up at the top, there's a force pushing down from the pig. And that's it. Nothing else is applying forces to the car. The helicopter, or I guess the rope technically, would show up if we did a free body diagram of the man. But as long as we're isolating the car, it doesn't show up. So the next step is we need to figure out the directions and what we know about the magnitudes of different types of forces. Rear. And here are the force types. So first, the weight force. Yeah. Yep, those are all the forces, because the only types of forces are weight and then contact forces. And now we've dealt with every place that there's contact with the boundary, so we know we're done. Yes, that would be a field force, a magnetic field force. Yeah, but so if that ever comes up in a, AP test problem or something, then, you have to include that the same way you include gravity, but we're not going to talk specifically about that. Yep. Friction is a contact force, that's right. It sort of depends on how fast, it depends on the speed that the car is moving, and so you're thinking the mud would make it more slippery or whatever, but that's not a real force then. No imaginary forces. Yeah, right. So, we don't have to worry about mud yet. Okay, so the types of forces are weight. That's the force applied by gravity. And that's going to occur in every problem. The second thing is pushing contact. Then pulling contact. And usually with pulling, we'll be dealing with cables. Cables being any kind of string, rope, any kind of thing that can pull, but if you try to push it, it'll just collapse. Friction. And then the last one that we'll deal with is the force applied by springs. Okay, so basically this is 4 very general types of forces, and then one that seems very arbitrary, right? Like you look around the room, you're like, I don't see any springs. I see 3 whiteboards. Why don't we do forces applied by whiteboards, you know? But the way that springs apply forces to things fits into a general category that actually does come up in engineering problems all the time. Essentially, when you talk about applying force to, like, a block of steel or concrete or most engineering materials, they behave mathematically the same way that springs do. Oh, you do have one, yeah. Right, there's a spring in every pen.
Not this one.
Ah, damn. But, so that's why we're doing the spring thing, because mathematically the way springs work comes up in a million ways in our everyday world. So for us, we're just going to do it with springs, but if you later go into engineering classes, and even later physics classes, this idea of spring force is going to be important. So now we're going to be talking about force types for quite a while. We're going to go through all of these one by one. The first one is the weight force. So how can we figure out what force gravity applies to things? That's a rhetorical question, but it's like a funny question. Like, I mean, we all know we can get on a bathroom scale or whatever, but before anybody had ever thought of stuff like that, how would you have any idea what force gravity applies? Yep. Okay, yeah. Okay, so, well, in this one, we are going to figure out the numbers. Mm-hmm. Uh-huh. But, like, in what way does the weight relate to mass? Like, it's a strange question, you know, like, yes. Yeah, you can do that, but, like, if we think, like, this is our starting point for figuring out the magnitude of forces, you know, it's a weird, like, philosophical question. Okay, how about this, though? So if you wanted to know what force gravity was applying to things, the easiest way to do it would be to find things that don't have anything acting on them but gravity and measure their acceleration, right? Because Newton's second law says the net force is equal to the mass times the acceleration of the thing. So let's think of objects where the only force is the weight. That's one example, I guess, in some cases. Yeah. Okay, so yes, that's the idea. So think of objects where the only force is the weight. And what have we talked about where the only force is the weight? Free fall. That's the definition of free fall. And what do we know about free fall? What do we know about the acceleration when something's in free fall? Yeah, so in that case, the acceleration is g, which is about 9.81 meters per second squared down. Okay, so let's think about the force. Okay, so first, let's think about what's the force on a 1 kilogram object. Okay, our chosen object is 1 kilogram. Then Newton's second law, if we choose a coordinate system with the y-axis up and the x-axis horizontal, the total force from gravity, the total weight force, is equal to the mass of the chosen object times the acceleration of the chosen object, which would be 0, negative 9.81. And you get 0, negative 9.81 with these weird units of kilogram meter per second squared. And this we give the name newtons because this is such a pain to work with. So 0, negative 9.81 newtons. Okay. So thinking about it that way, we figured out what force is applied to this object. Awesome. So is that the force that the weight applies to everything? So now let's think about, yeah. Okay, so now think of an object with the mass m in free fall. Then Newton's second law says the force applied by gravity is the mass of the chosen object times the acceleration in free fall, which is 0, negative g. And so you get 0, negative mg. Is that the force that, gravity applies to everything? Is that the force that gravity? Okay, so what we see here is that gravity has to apply a different force to everything based on what we know about free fall. So the weight is different for everything based on its mass. And it's equal to mg pointing down. Okay, now we see actually why this is why pinball in free fall is less affected by air resistance than a ping pong ball. So if you think of a ping pong ball and a pinball as being the exact same size and shape, the only difference is their mass. A ping pong ball has, that's supposed to be a ball, has an air resistance force, I'll call it F drag, acting up, and a downward force of little m g pulling down. A pinball has the same upward force F drag. It doesn't have less air resistance acting on it, but it has a bigger downward force from gravity. I'll call it capital mg. So even though they have the exact same drag force acting on them at a given speed, the drag force, it's easy for the drag force to be big compared to the weight force for the ping pong ball. And for the pinball, the weight force, until you get to a much higher speed, is so much bigger than the drag force that its motion isn't affected. Anybody have any questions about that idea? Okay, so the more mass, the more weight. Yes?
Gravity.
Yeah.
So like gravity. I thought gravity is the same for everything, but when I look at that, it makes me think that.
Okay. Yes. So that's a really confusing thing for everybody with this. Is like, okay, so this whole time I've been trying to really like be clear about the fact that for things in free fall, they behave exactly the same. Their acceleration is the same. They hit the ground at the same time if there's no air resistance, right? But now it's saying that even if there's no air resistance, the forces are drastically different acting on them. Well, what this showed is that the accelerations of things with different masses are the same. The acceleration is 0, negative g for everything. It's just in order to produce that same acceleration for everything, you need to have bigger forces for bigger masses. Because what mass is a resistance to acceleration. And if something's more resistant to accelerating, to get it accelerating at g down, you need to apply a bigger force. It's more resistant, you know. If you had to get a semi-truck accelerating this way with an acceleration of g, you'd have to apply a gigantic force. To get a ping pong ball accelerating that direction at g takes a tiny force. So yeah, that is, so it's still true that in free fall, everything accelerates the same, but it takes different forces on different things to do that. Any other questions? Okay, yes.
So does
Mass does not affect the air resistance force. And in our lab on air resistance, I gave you the formula for the drag force. And if you look, there's no mass in there. There's only surface area, a shape factor, density of the air, speed, okay? But there's no mass in there. What mass does is just determine how much the weight force predominates over the drag force. And so something with more mass, its motion is less affected by the drag force, even though its mass doesn't determine the drag force. Okay. Any other questions? All right, let's take a 10-minute break. Come back at 8:58. All right, so we talked about the weight force. I'll do a couple examples involving that in a second, but let me first talk about the next one, which is a pushing contact. Oh. And so when two bodies push against each other, so if one thing is pushing on another thing, then the vice versa is true too. Okay, like if you push against the whiteboard is also pushing back on you. Okay, you can't push on something that's pulling on you. Okay, so when two objects are in pushing contact, the force is perpendicular to the surface of contact and toward the chosen body. Okay, so for example, if you have two objects pushing on each other, I'll call this 1 and this 2. A free body diagram of ball 1 looks like this. Well, first there's going to be the weight force, M1 times G. And now we go around the boundary looking for contact. Where do the surroundings make contact with the chosen object? Yeah, bottom and right, exactly. So the ground is pushing up on the ball. So that force is perpendicular to the ground toward the chosen body. So, and I'll call that N I'll call it N1. N for normal force. Normal means perpendicular. But that's just any old variable. If you want to call it F or R or whatever, that's fine. And then over here, ball 2 is pushing on it. So that force is perpendicular to the surface of contact toward the chosen body. I'll call that R. And then a free body diagram of the second ball. There's a downward force, M2G. The ground's pushing up on 2, a different amount, so I'll call that N2. And then ball 1 is pushing on ball 2, so that force is perpendicular to the surface of contact toward that chosen body. It happens to have the same force R. I'll talk about why that is pretty soon. Any questions about that? So that's how pushing contact works. Okay, so now using these two ideas, let's think about how a scale, like a bathroom scale, measures weight. Okay, so there's the floor of the bathroom, there's the scale, here's you. That looked like Baymax. That's true.
Yeah, that's Baymax.
It's not, it's just.
So let's say that you have mass M. But the scale doesn't have any weight in. So what you're trying to measure is the force that gravity is applying to you. That's what you're interested in. The reason we're interested in that is because, you know, the weight is proportional to the mass. And so we're just trying to figure out how our mass is changing. But the scale has no way to measure the force gravity is applying to you. It has no idea, you know, like the scale can only measure forces that are applied to it. So let's isolate the person. So free body diagram of the person. And think about what forces are acting. There's a downward force from the weight. And now go around the boundary of the person. Is there anywhere where the surroundings make contact? The scale, and that's a pushing contact, so that's perpendicular to the surface of the scale toward the chosen body. Now, nothing else is making contact, so now we'll use Newton's second law. I'll use a coordinate system with the y-axis up. Free body diagram. Okay, so let's do Newton's second law just in the y direction. There's a downward force mg, an upward force n, and then what's the person's acceleration in the y direction? Just standing there, so the position's constant, so the velocity is 0, so the acceleration is 0. And so what this tells you is that that force N is equal to mg. And so the contact force with the scale equals the weight. Even though it's not measuring it directly, if those are the only two forces acting and the person isn't accelerating, then that has to be true. Kilogram meters per second squared is the same as Newton's. Kilograms from the mass, meters per second squared from the acceleration. Mm-hmm. Yep. Well, we'd have to use Newton's second law to see how big that n is. So the only one that we know the magnitude of is the weight. Everything else you have to solve for, but at least we know the directions of the other forces. Okay, gravity we know everything about. We know the direction and the magnitude. Okay, so here are some ways to make the scales contact force different from the weight. One is here's a side view. And here's the, and this is, here's the wall, is on the scale. No, well, you'll see why in a second. And here's the towel rack. Have you seen that Simpsons? Okay, so say the towel rack pushes up with 0.1 mg. Okay, so a tenth of your weight is held up by the towel rack. Okay, so then a free body diagram. There's a weight force of mg. There's a pushing contact from the ground of n. And there's a pushing contact from the towel rack of 0.1 mg. Then Newton's second law in the y direction says negative mg plus n, because that's in the positive y direction, plus 0.1 mg is equal to 0 because the person's not accelerating. And now do the algebra and you get that that contact force is equal to 0.9 mg. Okay, so the scale isn't measuring the weight. The scale's measuring the contact force. Let me... And then the second way is put the scale on an elevator. What? Let's calculate. Let's see. That's right. So let's do it for the elevator accelerating down at 2 meters per second squared. Or let's keep doing it in terms of g. So accelerating down at 0.1 g. You know, g is about 10 meters per second squared, so that's about 1 meter per second squared. Okay, so there's the elevator, there's the scale. Well, I'm just saying if you want to lose weight, this is one way to do it. So a free body diagram of the person, in this case, doesn't look any different than it did just standing on the ground. So the forces are the weight, mg, and then an upward force from the elevator. The free body diagram looks exactly the same as it did standing on the ground. Now Newton's second law and we'll just do in the y direction again, says negative mg plus n is equal to, this time the person does have an acceleration because the elevator is accelerating up. So the mass of the person is still m, and the acceleration of the person is positive 0.1 g. That's the acceleration of the elevator. And so what you get, again, is that the scale, that contact force, is equal to, did I say up or down? I said down and I drew it up. Let's change one of those. Okay, so then this would be negative. Since it's down, the acceleration is negative. And then the normal force would be equal to 0.9 mg. So if the elevator is accelerating down, the scale reads a lower weight. Yeah, if the elevator is accelerating up, you're gonna gain a little weight, unfortunately. So
The elevator was shooting down really, really fast.
okay, so that was the next thing that I was going to say is be really careful about when you're talking about acceleration and when you're talking about velocity. So an elevator accelerates briefly, and then it's just going with a constant velocity. If it's going, yeah, so I'll talk about that too. So yeah, exactly. So let's say that the elevator accelerates and gets up to a constant speed of 1,000 meters per second. It's, you know, going super, super fast. If the elevator is moving with a constant speed of 1,000 meters per second, what's the scale going to read? Just your weight, because constant velocity is zero acceleration. Okay. Okay, so now, yeah, like what's sort of the most extreme case here of how much weight you can lose by getting on an elevator is the same as the example of the vomit comet, the plane I was talking about. So what if the acceleration of the elevator was negative g? So it was in free fall, and say you did want to weigh yourself. Then this side would say negative mg. When you solve for n, the mg's would cancel, and you'd get that contact force was zero. You'd experience weightlessness, and that's the idea of these training things like the plane that goes through the parabolic path. And then what if the elevator was accelerating down at greater than g? You'd float. You'd start to lift up. You'd accelerate upwards. Compared to the elevator, you'd still be accelerating down at 9.81. Yes.
Whoa. That would be like your exact weight.
Yeah.
Also,
Do you know how astronauts weigh themselves in zero G environments? They do. They have to because astronauts lose bone density really quickly, and so they have to make sure they're not losing weight. And so the way that they weigh themselves is they use the definition of mass being a resistance to acceleration, and they shake them back and forth and measure how much force it takes to accelerate them a certain amount. That's how they do it, apparently. I've never seen a video of it, so I guess I wouldn't bet my life on it, but that's what they do. Because without gravity, you can't use any kind of scale, a balance or whatever. You can't use anything if there's no gravity. But you can see how resistant to acceleration they are. Okay, let me do one more example problem. Yeah, so let's say we have a horizontal, like, carousel thing. Guy? Okay, sure. Okay, so we're done with the scale thing. That's that guy again. And with his feet, he's holding a box. Yeah, exactly. And let's say that this distance is 1 meter.
Yeah, that's a box full of the Valentine tomorrow.
Yeah. And let's say that it's not accelerating. It has a angular velocity constant of 5 radians per second. And let's say that it's frictionless, so that box would slide, like this is made out of ice or something. Yeah, but he has a chair back behind him, but he's holding that box. If the mass of the box is 10 kilograms, what's the force required on the box so it doesn't slide? he's spinning, the box is spinning. And for a coordinate system, let's use X and Y that way. Okay, so I'm going to draw a free body diagram of the box. From above. There's a weight of the box going into the carousel. So I'll draw that like the tail of an arrow, 10G. There's a normal force coming out towards us. Who's with me so far? And then there's one more force acting. What would that be? That's the guy pushing it. It's just a pushing force, so that force is applied this way. I'll call that, well, I'll call it just F. Yep, question? This is from above, like a bird's eye view. So now the coordinate system is like this. So along the x-axis, the only force is F, okay? So Newton's second law in the x direction says negative F is equal to the mass times the acceleration. And now we just need to calculate the acceleration using circular motion. Okay, so what do we know about the acceleration? If that's the path of the box, its velocity is this way. Yeah, well, let me just label it with, so this is the velocity vector. The x is like feathers, so that's a vector going away from us. The normal force is coming towards us. Yeah, since this is a particle, it doesn't matter where I draw them, but so I'm just putting them in a place where you can tell what's going on. Is it speeding up or slowing down? Let's look at the problem. Omega is constant, so it's not speeding up or slowing down, so there's no tangential part. There is a centripetal part. So the total acceleration is just the centripetal. The magnitude of this is omega squared r, which is 5 squared times 1, or 25 meters per second squared. That's in the negative x direction, so the total acceleration it would, because r would be different. Right, it wouldn't be any different. Yep. Okay, so that's the acceleration. So now plug that into Newton's second law in the x direction. And we get negative F is equal to the mass times negative 25 And so F is equal to 250 newtons. So he has to apply a 250 Newton force with his feet to keep that box from sliding out towards the edge. Kilogram meter per second squared. Yep. A Newton is about a quarter of a pound. So you know, that's like 60 pounds of force. I mean, I guess that's a pretty big force. It's being spun very, very fast. Yeah, that's a very fast spin. Okay, so the way to think about it, don't think about it being pushed outwards. Think about it as in order to keep moving in a circle, it needs to have a force providing a centripetal acceleration. So for it to stay in a circle, a force needs to be pushing towards the center. If that force isn't big enough to keep it pushing towards the center, yeah, then it'll fly away. But it's sort of the opposite of the way you were saying it. The force is required to make the circle happen. Well, he needs to be applying that force of 200 newtons. If he doesn't apply that force, his knees will break his jaw, you know. But if he's not there, then the back of that chair would apply that force. And we could figure out, you know, what's going on with him by drawing a free body diagram of him. You'd see that there's a 250 Newton force on his feet, and since he's not accelerating, there's a 250 Newton force on his back, counteracting it. Yeah. Any other questions about that? All right. See you Friday.